Welcome to what I might call the latest episode of We Live in an Ancient Cosmos. Today, I'm taking a trip down memory lane and revisiting a post from a few years ago from my blog, thenaturalhistorian.com. That blog's post was inspired by a NASA press release from 2011. The press release made headlines because it referenced attempts to identify the source of the asteroid that might have been responsible for the extinction of the dinosaurs. But what caught my attention was the reference to the age of asteroid families. This got me thinking, what is an asteroid family, and how do astronomers even determine the age of these ancient space rocks? I did some digging, and the answers were really fascinating, and I hope they'll be fascinating to you as well. So join me as we rewind the clock of an asteroid family and delve into the world of asteroid dating and the clues they hold about the history and the age of the solar system. We've got that coming up. So, just what is this asteroid family thing? When we think about an asteroid belt between Jupiter and Mars, we might imagine it as a chaotic collection of space debris floating aimlessly in the vast expanse of the universe. However, the reality is far from this. Astronomers have measured and mapped the locations of over 100,000 asteroids in the asteroid belt. And through their analysis, they have discovered something quite remarkable. They found that certain groups of asteroids are related to one another and are referred to as asteroid families. These families are formed by having similar orbits, composition, the amount of dust that covers them, and a whole bunch of other factors that can be measured from right here on Earth with our telescopes. The asteroids in these groups are believed to have a common ancestor, hence the name asteroid family. And why are they a family? Because they're all descendants of a larger asteroid in the past that was hit by another object, causing it to break into multiple pieces, which became what are called daughter asteroids. Sometimes the parent asteroid is essentially destroyed or broken into many small pieces, for which no single one represents the bulk of the parent. And so all these are the remaining children that are left over from that broken original parent. In other cases, the parent asteroid might survive, or only 15% of the asteroid is broken off, and we see the family remnants as being the daughters or the surviving elements that are broken off of that original asteroid, and we might know which is the original asteroid based on a bunch of different calculations that can be done. What you're looking at here is an artist's conception of the breakup of an ancient asteroid, this asteroid called Baptistina, into a whole bunch of remaining family members, which we visualize today. This is actually the asteroid that was mentioned and talked about in that original NASA article. So there's a method, though technically challenging, to estimate the age of asteroid families, like this family called Baptistina, by measuring the orbital characteristics of many members of the family, such as the direction, the speed of the remaining or daughter elements that are left. Scientists can infer when all the family members were once part of a single parent, the parent asteroid. In the case of the Baptistina family, this method has been used, and the family is estimated to be about 80 million years old. In other words, it's been 80 million years since all these individual parts were collectively one whole piece, the parent. It's important to note that this is the age since the breakup, all right, since the event that caused these parts to separate, not the actual age of the material of the asteroids themselves. Now, this might sound really old, 80 million years, but it's nothing like what most of the parents are thought to be, which is somewhere on the order of potentially billions of years old, being the remnants of the origin of the solar system itself. The asteroid belt between Mars and Jupiter is home to many different asteroid families, each with their own unique characteristics. So let me show you a few of those. What this figure represents is sort of on a two-dimensional figure, shows a large assortment of bodies that have been identified of those 100,000 asteroids that we have mapped right in the asteroid belt. And what you'll find is, as I said before, they're not just randomly distributed across the asteroid belt, but they come in, many of them are in groups of asteroids that are relatively close to each other. The scale across the bottom there on the axis is the astronomical units, and 1 astronomical unit, in other words, between 2 and 3, would be 93 million miles. So the groups that you see here, the bunches of the different colors, represent lots of different objects which have been identified as all being probably part of the same family. And those family members are relatively close to each other. Now, when I say relatively close to each other, some are separated by 10 million miles, right? Because one astronomical, well, I think I said 1 astronomical unit is 93 million miles across. And so the dispersion of asteroids are in these sort of clumps, or you could think of them as clouds. Although they're not really spherical clouds, you can't see that on this figure, but they're typically in sort of a V shape. And so they're you can think of them as they're scattered, all right, from, if you imagine an initial parent, and then you have something large that hits it, all right, depending on the direction it hits it, it's going to spray out, right, the daughter elements, the broken parts. And they're going to be traveling at various speeds, but most likely in sort of this V-shaped pattern going out from that moment of axis. And that's one of the pieces of circumstantial evidence that these are actually daughters of an original parent, is the direction at which all these different objects are flying, because all these can be measured, as they have been measured, and we know the orientation and the speed they're flying through space. So let's just talk about one particular family. It's actually a family that's not shown on here because it's fairly small, but it's been studied in great detail. So this family, called the Charon asteroid family, it's particularly interesting, or at least particularly interesting for what I want to talk about and why we're talking about this here. And it's interesting because we have a lot of information about it. There's over 90 members that have been identified from this family. But what's even more impressive is that 13 of the individual asteroids have had their orbits very carefully mapped. In other words, they've been watched for fairly long periods of time. Many, many different measurements have been taken of them over a series of many years. Using the maps then of their locations, of their speeds, all right, how fast they're moving through space, scientists have been able to run the orbital patterns backwards in time, allowing them to determine when all 13 pieces would have come together as one. The calculation yielded an estimated age of the parental asteroid as being just 5.8 million years ago. In other words, this is a fairly young family. And the amount of error they suggest in their estimate is only 0.02 million years. All right, so 20,000 year error. So 5.8 million years, plus or minus about 20,000 years. This makes the Charon asteroid the youngest known asteroid family in the asteroid belt. So all those other families that you're seeing on this particular figure are all calculated to be much, much older than this. If the Charon family were actually on this particular figure, it would take a lot less space because the particular fragments have not had as much time, and so they have not scattered quite as far. They're not tens of millions of miles apart. Now, what's really impressive here is that if you have 13 individual asteroids, and each of them is moving at a different rate, they're not all moving at the same rate. You know, if you have an object hit another object and it breaks apart, some parts are going to have had more energy, all right, depending on the mass of the particular piece that's being moved. And they're going to move away from the original parent at a faster speed than another one. And so what's really cool is that here you measure 13 different objects that are all moving at different speeds, but they're at different distances from each other. And if you back calculate, you look at where was that object 10 years ago, 100 years ago, 1,000 years ago, 10,000 years ago, 100,000 years ago. You start to move all those pieces closer and closer and closer and closer together. And it turns out all 13 of those things all converge at the same point in time in the past. And so that's remarkable evidence that all of them actually are family members, right? They all are related to the original parent asteroid. So another evidence of the particular youth of this particular asteroid family is due to the lack of dust buildup on them. The more dust that builds up on the asteroid, the more dingy, right, it looks in terms of how the light bounces off of it. And so that's another aspect of all these different asteroid families, is the ones that are the oldest, right, are the sort of the dirtiest and the grayest of all of them, and therefore are actually harder to see in many cases. The members are also, the younger they are, as we just noted, they're much closer together in space. Whereas the older ones have had what? They've had more time for the daughters to be running away from the original parent. Okay, they've made it farther and farther away from each other. Now, it's really important to note, however, that if you give it enough time, let's say that it was 100 million years ago that this object, the parent, was smashed into smithereens, and the daughter products are the family members are running away from that original element explosion. At some point, 50 million years, 100 million years later, they're so far apart from each other, it'd be very difficult to identify them as being part of the same family, and they would just start to look like a random jumble of asteroids. And surely there are many, many asteroids in the asteroid belt which appear to be lonely, all right? They don't appear to be related to any other asteroid. They're so far apart from others and don't look like others. But in fact, they may just all be really old families that no longer are easy to identify as families. And so we're only able to see these more recent ones. But of course, I'm using the word recent here, but in the case of recent, the most recent identifiable family is 5.8 million years old since that event occurred. So now all of this has really been prologue to talk a little bit about what is the meaning of asteroid families within the perspective of a young Earth worldview. See, young Earth worldview is not just that the age of the Earth is 6,000 years old, therefore it's a young Earth. Typically, almost all young Earth creationists are also young age universe creationists, right? Or young universe creationists. So I think asteroid families are a powerful indication of the ancient age of the solar system. I find the evidence of the long history of our solar system, as seen through asteroids and other planetary features, to be a significant challenge to the young Earth creationist perspective. When faced with geological features on the Earth that appear old, young Earth creationists often rely on the explanation of a recent global flood, such as Noah's flood, to explain the rapid layering of rock and billions of fossils found within it. However, such explanations, Noah's flood, are not really possible for features that appear to have developed over millions of years out in space or on other planets. I've talked about Mars in the past and its features. Asteroid families and rotating asteroids, as seen in the case of my blog post that I will put in the links below. I have a blog post named As the Asteroid Tumbles, Asteroids in the Age of the Solar System, which looks specifically at the question of asteroids that are tumbling around and how we can calculate based on the tumble how long they've been tumbling or since when they've been struck. So it's very similar to this particular example. These can be particularly challenging to the notion of a young solar system because their age can be estimated through simple mathematical extrapolation. For example, by measuring the speed at which pieces of broken asteroid are drifting away or apart from each other, we can calculate the age of the asteroid family to be tens of millions of years, just as we have shown and done here. If the solar system were young Earth creationists would have to respond to this evidence of the great age of the solar system in what I think is one of three ways. Here's the three possibilities. First, they'd have to deny that asteroids were part of the family or part of a family. They'd have to claim that the characteristics that suggest they're related, such as their orbits and their composition, are just coincidental. They would argue that each asteroid was created individually and had no relationship to each other. They'd have to point to the trajectories, the speeds at which they're traveling. And even though those speeds might be calculated to bring them back into connection with one another, they'd have to say that God simply created them as they are, the way that we see them. Second, they'd have to accept that the asteroid families represent the daughters of a parent breakup, but claim that this breakup occurred within the past, 6,000 years. This would require that the speeds at which they are drifting apart from one another have changed greatly over time, and that they have achieved the vast distances between them we see today by traveling at incredibly high speeds in the past, and then suddenly slowing down to the current speed at which we actually observe them, right? The observable evidence. However, it's unclear what exactly would change the speed of these asteroids when they're out there in the depths of outer space, where there's virtually no friction, leaving only supernatural intervention as the only possible explanation. Third possibility is they could accept that the asteroids really are a part of an asteroid family, but employ what's called the apparent age defense. This proposes that God created the pieces of these large asteroids in their present orbits to appear or look as if they were once had a common ancestor. But they never actually did have a common ancestor in real time, but only in apparent time, apparent age. Young Earth creationists like Henry Morris have tried to make a distinction between what he calls essential appearance of age and what he calls deceptive appearance of age. The former would include the necessary appearance of age, like a full-grown human, appearing to have grown from a baby, while the latter would include the false appearance of age, like a star appearing to have exploded when it never actually did. Now, I actually find it very difficult to understand the real distinction that's being made here. It's hard. I've never been clear about how a young Earth creationist should distinguish between essential age built into the creation and deceptive age, which isn't allowed to be built into the creation. My best guess is that essential age for, say, astronomical features like light coming from a star that is created old, that's fine. You know, it's light, it looks like it comes from that star. But if that information recorded an explosion of that star, but that star hasn't, never really exploded, it simply was built into the light coming here, well, somehow that's not okay, because that would be considered deceptive age. This deceptive age, which refers to false evidence of an event or history, is not acceptable in the minds of many young Earth creationists, and is a pretty effective argument that non-creationists have used against them. In the case of these asteroid families, a group of asteroids with orbits and characteristics that suggest a past history as a unified object millions of years ago would, I think, be considered deceptive. If this is considered deceptive age, then the third explanation for a young solar system is just not viable. This leaves only the possibility of number two, that there's changing rates of motion over time, possibly due to what? Changes in physical laws, or denying the existence of asteroid families as explanations? None of these options provide straightforward or reasonable explanations for disregarding evidence of an ancient solar system. So where does that leave us? This NASA article report of an 80 million year old asteroid family, it just adds one of hundreds of thousands of examples or a growing body of evidence, which Christians they're presented with on a daily basis if they were to look for it and they were to see these types of things and think about them, that support the ancient age of a solar system and of the universe itself. Much of this evidence is based on really simple processes that are most easily understood within an old age framework. Young Earth creationists often try to reinterpret this data to fit or squeeze into this young universe model. But in doing so, they have to generate a whole bunch of ad hoc hypotheses. When faced with no viable explanation, they might resort to finally claiming that NASA has a bias and that the data doesn't support this, or it's suspect, or there are liars there, right? It's all a conspiracy. This, however, requires the acceptance of, again, a large-scale conspiracy to distort data and its interpretation. And this would also involve a large number of Christians who work for or with NASA on numerous projects. Asteroid families might not be the absolute 100% conclusive, ironclad proof that the solar system is older than 6,000 years. But nonetheless, they should certainly give pause to those of a young Earth creationist persuasion. causing them to at least reassess their convictions and question whether their young universe view is truly supported by Scripture, or if, in fact, it has become an extra scriptural article of faith imposed on Scriptures by human interpretation. Whenever we rewind the clock, we look at things that are occurring today and we trace back them in time, we almost invariably find that we need more time than 6,000 years in order to squeeze them into history. This example is as simple as being able to predict where the planet Earth was 4,000 years ago. We know the rate at speed at which it's traveling. We could predict just where it was with high degree of accuracy 4,000 years ago, 6,000 years ago, 10,000 years ago, or 100,000 years ago. We can predict, astronomers can tell you, what would the sky have looked like when Egyptians looked up and saw the stars? When Abraham looked up and saw the stars, what stars did he see and where did he see them on the horizon on a particular day? Why? Because we know where the Earth would be, where an individual would be, what sky they would be looking at any particular time in the recent past. And by recent, I mean tens of thousands of years. Of course, it's not going to be quite as accurate if you looked at 100,000 years. Nonetheless, these asteroids can be mapped with great precision in terms of their speeds and trajectories. And simply rewinding the clock allows us to get back to a moment in time, a moment in which there was a dramatic event. Not as dramatic as an asteroid striking the Earth, but nonetheless, one asteroid striking another, causing the eruption of one asteroid into many, many parts, which then begin to float away from one another. And all we have to do is rewind the clock to see those particular events in the past. We don't have to have been there to have really a high degree of precision in our knowledge of past events such as this. And when those numbers, right, those ages come out to be hundreds of thousands of years or millions of years, using just calculations that you could do on a calculator at home, that's something that must be considered if you think that the world or the solar system is only 6,000 years ago. You have to be able to address information as simple as things like these asteroids. Well, thanks for hanging out with me. Appreciate your attention. Hit the like button, subscribe to my channel. I'll be back with lots of other interesting stories, or what I hope are interesting stories. Thanks a lot. We'll talk to you later. Bye-bye.